Good morning, class, and welcome to our continuing lectures on sustainable energy technology. In the last class, we started our discussion on solar energy, and we were beginning our discussion on solar energy and how solar energy is being used in the world today by looking at how we can measure the amount of solar energy flux that is available in different parts of the world and how it varies with the change of seasons, with the different hours of the day, and as we will see, with the change in orientation of the solar collector surface on which the solar flux is incident. So just to recall, in the previous lecture, we discussed something called the declination angle, delta, which is nothing but the angle between what the sun subtends at equinox and the sun subtends on any other day during the noontime. And the definition and the equation for this declination angle was given by this expression here, where delta 0 was 23.44 degrees, and this is sine of 360 degrees into 284 plus n by 365, where n is the number of days in the year, the day number of the day. So suppose you want to evaluate the declination angle on the 1st of February, that will be the 32nd day of the year, because January has 31 days. So February will be the 32nd day of the year, and you put n equal to 32. So whatever that value comes here in degrees, sine of that multiplied by delta 0 will give you the declination angle on that given day. Given that you know the declination angle and the latitude angle for that given location, and in this point remember the latitude angle varies from plus 90 degrees in the northern hemisphere to minus 90 degrees in the southern hemisphere. So equator to 90 degree north is equator 0 to plus 90, equator to 90 degrees south is 0 to minus 90. Then the number of daylight hours on a given day in a certain location at a specific latitude angle is given by this expression, 2 by 15 cos inverse of minus tan psi tan delta, okay, where psi is your latitude angle and delta is your declination angle for that day. Now this cos inverse of this term, now cos theta varies from plus 1 to minus 1. Okay, so when cos theta is plus 1, then cos inverse 1 is 0 and the number of daylight hours is 0. What this means is you have perpetual darkness. This usually happens in the winter beyond the Arctic Circle. So under any condition, if you find that your minus tan psi tan delta value is greater than 1, then you have 0 daylight hours in that region. So greater than or equal to 1, this value becomes 0 daylight hours in that region. Similarly, cos of minus 1 is basically 180 degrees. Okay, so when you put cos inverse of minus 1, then this becomes 180 degrees, then 15, then 180 into 2 is basically 360. 360 by 15 is 24. So you are getting 24 hours of daylight. Okay, so in any condition where minus tan psi tan delta is less than minus 1, it means we have 24 hours of daylight. Okay, which is perpetual day, which happens in the beyond the Arctic Circle in the summer months. Anywhere in between, we have 0 to 24 hours of daylight in that location. Now that we know how to evaluate delta and the number of daylight hours, we have to evaluate what is the angle that the sun is subtended on a solar collector which is inclined at a certain angle beta with respect to the ground. If you look at solar collectors, whether that is used for solar water heaters or used in solar PV farms, the solar collectors are always oriented at a certain angle with respect to the ground, and this angle is what we call as beta. So given that the solar collector is oriented at angle beta, and given that the inclination of the sun at a given point of time with respect to the ground normal is theta z, we can also define another angle theta, which is the angle between the normal to the solar collector surface and the sun. So if this is the sun's rays, this is the normal to the collector, this angle is theta. So we can get a better idea of the main different types of angles that are important in figuring out the amount of flux that a solar collector can absorb in a at a given time of the day. So this is our ground. This is north, south, west, east axis. Okay. So this side is north, this side is south, this side is west, this side is east. And the solar collector is inclined at an angle beta with respect to the ground, as you can see here. Okay. Furthermore, this solar collector is not pointing directly in the north-south direction, but is inclined at a certain angle with respect to the north-south direction, and this inclination angle is gamma. Okay. This is called the surface azimuthal angle. We will discuss this in more detail later. This is the normal to the to the solar collector surface. So this is the normal to the solar collector. This is the normal to the solar collector surface. This is where the sun is. So the angle between these two is theta. This is the angle of incidence, angle between the solar beam and the surface normal. The zenith angle theta z is the angle the sun makes with respect to the ground normal. Okay. So we have theta z, theta, beta, and the surface azimuthal angle gamma is the angle that this surface normal makes with respect to the north-south direction. Okay. So in the west, if the surface is oriented westwards with respect to the north-south direction, then gamma varies from 0 to 180 degrees. So surface can be rotated like this up to the other side. Okay. Similarly, if the surface is rotated eastwards, then the gamma varies from 0 to minus 180 degrees. So the surface can be oriented like this. This is 0 degrees, so exactly north-south direction. It is moving like this. Then there is an angle gamma, and the surface is oriented east of the north-south direction. So in that case, it's plus gamma is 0 to 180 degrees, eastward 0 to minus 180 degrees, and westward it's 0 to 180 degrees. Okay. So this is called the surface azimuthal angle gamma. Given these values, we can evaluate the value theta at any given time of the day. So let us see how that is being done. The first point we have to figure out is what is called the hour angle. Okay. So this hour angle is the angle through which the earth has rotated since the solar noon at that location. Okay. Remember, there is 24 hours in the day, and the sun rotates one full circle in 24 hours. Basically, the relative motion of the sun on the sky is one full circle in 24 hours. Correct. So one full circle is 360 degrees. 360 degrees by 24 is 15 degrees. So in 1 hour, the sun appears to move by 15 degrees on a given day. Okay. So this hour angle is the angle through which earth has rotated, or with respect to earth, sun has moved since the solar noon at that location. And this value omega is given by 15 degrees into the local time, the time at that location minus 12 hours plus the difference between the longitude value of that location minus the longitude value of that time zone. Let us understand what this means. Okay. Suppose every country has a local time, has a standard time given by a standard longitude. Okay. So all over India, despite the fact that the longitude values are different, you have the same time because we have standardized the time at a given time zone, at a given longitude. Okay. Suppose you are on that longitude, then your official time is the same as the local time. Okay. The sun will be directly at its highest point in the sky at 12 noon. Okay. So then this psi minus psi star time zone, which is the longitude correction, does not apply. Okay. Then you have only just 15 degrees into time of your location minus 12. How does this work? Suppose it is 4 p.m. in the afternoon. Okay. Now clearly 4 hours have passed since noon time. Alright. So the sun has rotated by 15 into 4, 60 degrees from its noontime location. So you can find this directly. 4 p.m. is 1600 hours. So you put 16 here minus 12 here. So 15 into 4, 60 degrees. So you get the hour angle. Okay. The problem comes when your position is not the standard longitude for your country. For example, as you understand, sunrise in Kolkata and in Mumbai happens at different times. Similarly, the sun is directly at its highest point in the sky, not at 12 noon, either in Kolkata or in Mumbai, because the local noon time is different from the standard Indian noon time, which is given by a different longitude, which is the time zone of India. So, suppose you have a city. It has a certain longitude value. That longitude value is this one. And the xi star time zone is the longitude value of your country's time zone. That difference gives you the correction in the hour angle that happens because your local time is different from the standard time of your country. So this xi is longitude. Remember, omega is less than 0 in the morning, greater than 0 in the afternoon. And also, meridian values are negative if the meridian is a west meridian. So your longitude will be given as either say x degrees east or x degrees west. East and west in terms of the UK longitude, which is Greenwich longitude, which is 0 degrees. Okay. If your meridian values are west of the Greenwich longitude, those values are negative. And if your meridian values are east of the Greenwich longitude, then these values are positive. So you have to keep that in mind. Now that you have evaluated the hour angle, how much the sun has moved from your local noon time, you have the values of beta, gamma and theta z, and you have the number of daylight hours and the declination angle delta. Now you can use this formula to evaluate the angle theta, which is the local angle of incidence for your flat plate collector. Remember, what is theta? Theta is the angle that the sun makes with respect to the normal to your solar collector at any given point of time. And how is this evaluated? This gives you cos theta, which has 3 or 4 constants, and we will show what they are. A minus b sine of delta plus c sine omega plus d plus e cos omega into cos delta. Delta is your declination angle. Omega is your hour angle. Okay, so these are very clear. A is sine xi cos beta. Xi is your latitude angle. Beta is the angle of your collector with respect to the ground. B is cos xi sine beta cos gamma. C is sine beta cos gamma. D is cos xi cos beta. E is sine xi sine beta cos gamma. So a lot of geometry, but these are the main angles. Longitude and latitude angle, the angle of the collector makes with the ground. Gamma is the north-south or east-west, the east-west inclination of your collector with respect to the north-south direction. So these three. Suppose, these are the values of A, B, C, D and E. Now suppose you have a special case when your angle of inclination of your collector is the same as your latitude angle. So here, this is how your collector looks like. This is your latitude angle at your location, and your collector angle is the same as the latitude angle at your location. Okay. So, and your gamma is 0. That is, your surface is oriented directly in the north-south direction. Then all of these, lot of these values cancel out, and your cos theta just becomes cos of your hour angle and cos of your declination angle. Okay. And in many cases, this is the preferred orientation direction, because as we will see, show that the solar insolation values are highest when your flat plate collector is oriented in your local latitude angle value. Okay. For that case, this simple formula will work, and then your solar flux is the normal flux into cos theta. So G equals to G star cos theta, as we discussed earlier. So this is the total solar insolation in terms of megajoules per meter square per day for a location for various values of beta. Okay. So beta equal to 0 means the collector is perfectly horizontal to the ground. Beta equal to 90 degrees, collector is vertical with respect to the ground. And in this case, your latitude angle is 45 degrees. So beta is 45 degree means your collector is at an angle 45 degree with respect to the ground, and which is equal to your latitude angle value. Then you have 30 degrees and your 60 degrees. Okay. So if you see the situation where beta is 30 degrees, what you find, beta is 0 degrees, what you find is that there is a large variation in the amount of solar insolation collected by your solar collector between the winter time, that is January, February and December, and the summer time, which is May, June, July, August season. The insolation value was 20 megajoules per meter square per day in summer, and less than around 5 megajoules per meter square per day during the winter times. So there is a 4 times difference in the amount of solar energy received by this collector, which is flush with respect to the ground. Okay. At 30 degrees, this difference is changing. You can see the maxima has decreased to somewhere around 18, and the minima has increased to around 11. Okay, so that difference in the energy being collected has changed significantly. Okay, and also if you see the total energy is basically the area under this curve, and you see the total energy being collected has also increased significantly because this additional area has been added and this small area has been removed. Okay. At 40 degrees, 45 degrees, this situation is even better. Yes, there is a small decrease in energy here, but here you can see it's compensated by increase in energy collected in this area. So at 45 degrees, the differences are quite low. It's around 15 megajoules here and around 12 megajoules per meter square per day in the winter times. Okay. After this point, the differences decrease further at 60 degrees, but now the loss in energy is much larger in the summer times than in the gain in energy in the winter times. So the total energy being collected has decreased, even though the energy is now reasonably uniform, the energy collected both in winter and summer times. Okay. And at 90 degrees, so it's just like a window, the opposite is the case. You are getting more energy in winter times and less energy in the summer times. So all of this is a function of how the solar plate collector is oriented with respect to the sun. Okay. In winter times, the sun is very low on the horizon for most times of the day, especially in the high latitudes like 45 degrees. Okay. So a 90 degree collector is going to collect more of the sunlight in winter times because it is seeing the sun more often than not than in the summer times when the sun is directly overhead. So the angle of inclination is usually much larger. Okay. Whereas it's the opposite case for a ground collector, because in winter the sun is low on the horizon, the theta value is much larger. So G cos theta, the cos theta value decreases. So you have a large discrepancy in the winter versus summer. At 45 degrees, the discrepancy is much less because the sun, the collector is oriented such that it catches both the low sun during winter times and the high sun during the summer times reasonably well. And that is because it's exactly at the latitude angle. So at the equinox, the sun at noon time hits the solar collector flush at 90 degrees. Okay, so it is well balanced on both sides. Okay, that is why solar collectors are often oriented at its local latitude angle for that given location. Okay. Now the hourly variation of direct horizontal solar insolation. So this value here, horizontal solar insolation, is given by GH max sine pi T prime by N watt per meter square, where T prime is the time after sunrise. Okay. This GH max is the maximum insolation which is obtained at noon time, and this is T prime is time after sunrise. Okay. And this actually works, and N is the number of daylight hours that is present on that day. Okay. So then the total energy collected by absorbed by a horizontal collector is integration of this over the number of daylight hours, which gives 2n by pi into the solar insolation at noon time into 60 into 60 joules per meter square per day. So this value is basically being plotted here for different values of N and different values of GH max. Okay. So this kind of gives you an idea of the optimum way to orient your solar collectors and how to evaluate the angle theta that is used to evaluate the local solar flux at any given time of the day for differently oriented solar collector plates. Let's look at an example which will help to clarify many of these issues for us. So let us calculate the angle of incidence of a beam of radiation coming from the sun on a surface located at Glasgow in Scotland, which is at 56 degrees north and 4 degrees west at 10 am on 1st February. Okay. So the latitude and longitude are given. This is the latitude, this is the longitude. The time of day is given and the date is given. Assume that the surface is oriented 20 degrees east of south, 20 degrees east of south, and tilted by 40 degrees to the horizon. So beta is 40 degrees, gamma is 20 degrees east of south, and the local time zone meridian is 0 degrees. So xi of time zone is 0 degrees because it's in UK. Okay. February 1 is day 32 of the year, as we discussed earlier. So the declination angle is delta 0 sine 360 284 plus 32 by 365. We do this. This is 311 degrees. So this is minus 17.5 degrees. Say the declination angle is negative. Why is it negative? Because this is still in winter time. So the declination is towards the south, and southern movement of sun is negative. So this value is correct. So this is a good sanity check that you are on the right track. The hour angle we have to find next. The time is 10 am. So this is 10. The time zone is 0. And Glasgow time zone is 4 degrees west. Glasgow meridian is 4 degrees west, which is minus 4 degrees. Remember, the westward meridians are minus, eastward meridians are plus. So this is 15 degrees into the local time zone minus 12 plus xi Glasgow minus xi zone. So 15 degrees into 10 minus 12 plus minus 4, which is minus 34 degrees. Again, the sign is correct because this is before noon time. So you expect it to be negative, the hour angle. Now your latitude is 56 degrees. Your gamma, it's east of south. So gamma is minus 20 degrees. This is your beta, right? Beta is 40 degrees. Okay. So now you can find A, B, C, D and E directly. So E is 0.5, A is, you just put the values and you get A values, B values, C values and D values. And then you get your cos theta value. Cos theta then becomes this expression as we just discussed, this expression here. So this is the expression that we will use. Putting that on the expression, we get cos theta is 0.783. So theta is 38.5 degrees. So the angle between the sun and the normal is 38.5 degrees at that point of time. Then the local flux is G star cos theta. So if you know G star, you can find the local flux in watt per meter square. Okay. So next, so this kind of completes our discussion on our solar energy that is available.